Okay, third day of 2.1, looking at the derivative and the tangent line problem again. This has been quite the lengthy lesson. We're going to finish it today though. So let's start like I always have on these by drawing a graph. So I know I'm skipping the stuff up top. I'll come back to that in a second. Okay, so let's graph a function that looks like this. I feel like we've used this a lot before. And let's call a point over here. Let's call this C. So if that's C, then the ordered pair is C f of C. And then let's call this point over here X. So then this ordered pair is X f of X. Okay, I want the rate of change at C. So I'm going to jump back and forth between the box up above. Look, I'm asking you for f prime of C, which means the slope of the tangent. Okay, so I am looking for the tangent line. So let's draw that in. I'm looking for this slope. Okay, that's my plan. Okay, but remember we need 2 points. So what I'm going to do is I'm going to draw my secant line in, and now we'll label kind of what we want and what we have. So we want the slope of the tangent. We can find the slope of the secant because we have 2 points and we know how algebra 1 works. So if you look up above here, let's circle this. Look at this right here. This is algebra 1 slope. Look at, we're finding f of x minus f of c, so change in y over x minus c. Now remember when we looked at that visual a couple days ago, we focused on turning the secant line into the tangent line. So what we plan on doing is taking this little point here and dragging it up here. As we drag it, so if I draw it, let's see, I'll wait till that goes away. If I were to draw a point here, this would be the secant line. If I had a point here, this would be a secant line. And you can see the secant line starting to turn into the tangent line. Okay, so that's our plan. This is going to give you a numerical answer. Remember, my vote was to always find the derivative like this with x and then sub our x in at the end. This is giving us a numerical answer. So like I said, we're only going to use this when we're told to. So the directions might say find the alternative, or using the alternative form of the derivative, and then you'll have to do this. If they don't say, then we can find the derivative in general, like I just mentioned. Remember though, limits only exist if the left and right limits are equal. So we would need the limit as x approaches c from the left, and then we'll take that subtraction. We would need that to equal the limit as x approaches c from the right. And then same thing. Okay, so just a reminder about limits. So a lot of times too, if they ask for left and right derivative, that will mean to use the alternative form. Okay, if you're finding the left or the right derivative, we'll have to use this form. Okay, so we'll keep our eye out for that. Remember this piece right here is the slope of the secant. So that piece is looking at this. What we're doing though is we're dragging x to c, and by doing so, our secant turns into the tangent. Okay, so that's really it for theory. Let's just do some problems. So number 1, let's do this one together. Use the alternative form. Very clear that we have to use this form. Okay, so because it said use the alternative form, we're forced to use this new method. And to find the derivative at x equals -1, notice they said if it exists. So we're going to talk about what that means also. Okay, so to use the alternative form, we're going to say f prime of -1, the derivative, is going to be the limit. X is going to approach -1, and we're going to take f of x minus f of -1 all over x minus -1. We're going to write limit every single time. F of x is just the problem itself, which is x cubed plus 4x. Then we are going to sub a -1 in. I'm going to put brackets around the whole thing, and then we're going to sub a -1 in there, all over x plus 1. Okay, going on. We're going to get the limit as x approaches -1. That's x cubed plus 4x. And then look at this inside stuff here. This is going to be -1 minus 4, which is negative 5, but then I have a negative here, so now we have a plus 5. Now, right here, if we try direct sub, you're going to find out that you get 0 over 0, which is indeterminate. Indeterminate means more work. This looks like it can factor, but that doesn't look like it's easy to factor. But what you can note is you can expect x plus 1. Can't we expect this to be a factor of the top? That's almost what's always happened, so that they can cancel. Well, if I know that x plus 1 is a factor, then x minus 1 is a solution. I'm sorry, then x equals negative 1 is the solution. Okay, so if I know negative 1 is going to be a solution, we can use synthetic division. Let's see if you remember this. You can put negative 1 in the box. You write your coefficients of this numerator, which is what we're dividing into, right? We could also use long division and divide out this whole thing right here, but I'm guessing you don't want to do that. So again, we're expecting the top to have an x plus 1 as a factor, which means negative 1 is a solution. So we're going to write down the coefficients, which is 1. Notice that there's nothing being squared, so we need a 0. We have 4 and 5. A reminder of synthetic division, the 1 drops down, and then you multiply these two, and you get negative 1. So then you write negative 1 here, you add up the column. You do it again. You multiply these two, and you get 1. You write 1 here, you add up the column. Hopefully you're remembering this, and you get negative 5, and looky here, great news, synthetic worked. So what this means now is that x cubed plus 4x plus 5 can be written as x plus 1. Again, the reason I know that is because I have negative 1 here, so x plus 1. And then I can go ahead and write this. Now, this was to the third power, so that means our answer is going to be to the second power. And these numbers right here are our coefficients. So I'm going to have x squared minus x plus 5. Those are the same. So now, because my whole goal was to be able to factor and cross things out, I can rewrite the numerator as x squared minus x plus 5 times x plus 1 over x plus 1. The x plus 1's cancel, which is exactly what we expected. We can now use direct sub. Notice I'm writing limit every single time, and we have x squared minus x plus 5. If you use direct sub here, you're going to get 1 plus 1 plus 5, which is 7. Okay, so that's the alternative form. It's another way to do it. Again, the only real reason that we are doing the alternative form here is because they told us to in the directions. Okay, let's review what this means. So this means that the derivative at negative 1 is 7. It means that at x equals negative 1. This is just a reminder, like a refresher about the concepts. We're really done once we got this as our answer. Okay, so let's just review real quick. At x equals negative 1, f of x has an instantaneous rate of change. That means at that moment, the rate of change is 7. It also means that the slope of the tangent line to f of x at x equals negative 1 is 7. Okay, so just a reminder with you about everything that we're finding and how it's related. Okay, like I said earlier, there's just a handful of examples here that we're going over. The concept is pretty straightforward. Again, looky here, alternative form that they're asking us to use. Okay, so why don't you hit pause, try this one on your own, and then we can go over it. Okay, I'm going to keep going, but if you could pause it and try it, that would be awesome. Okay, so the derivative at 1, it's the limit. Notice earlier, too, I wanted to point out, we don't have h going to 0 because we're not setting it up that way. We're letting x go to 1. Okay, and then it's just secant, f of x minus f of 1 over x minus 1. We can go ahead and replace f of x with x over x plus 1. We can replace f of 1 by subbing 1 in and get 1 over 1 plus 1, which is 2, all over x minus 1. If you were to try direct sub, you're going to get 0 over 0. indeterminate, which means more work, this is going to be the problem that we want to get common denominators. So we have to multiply this first fraction by a 1/2, and then we have to by a 2, and then we have to multiply the second fraction by an x plus 1 over x plus 1. Okay, so let's go ahead and write that. We have x over x plus 1, and this is going to be multiplied by 2 over 2, and then we are going to have a 1/2 multiplied by x plus 1 over x plus 1. And notice here I'll have to squeeze it in. The whole bottom is x minus 1. Okay, going on, the limit as x approaches 1, we have 2x minus, let's make sure we keep those separate. I'm going to put parentheses there just so it doesn't look messy. I'm going to distribute the -1 to everything. So that is going to give me negative x minus 1 all over a 2 times x plus 1, which is the bottom. And then look here, don't forget about this x minus 1 down here. But again, like I've been doing, instead of dividing by that, I'm going to multiply 1 over x minus 1. As I go to write this again, I'm going to get as my numerator x minus 1. And then the denominator, I can multiply this by this. There's just a 1 up top, so that's why it's just x minus 1. Okay, so the bottom now is 2x plus 1, x minus 1. Oh, here's where we're good. Go away. Now we'll no longer get 0 in the bottom. So then I get the limit as x goes to 1, 1 over 2x plus 1. If you replace x with 1, you get 1/4. So f prime of 1 is 1/4. Again, this would not have been my choice. I would have rather used this formula, limit as h goes to 0 of f of x plus h minus f of x over h, which would have given me the derivative at x. Then I could have subbed my number 1 in because they asked for 1. Okay, but they did say alternative, so we had to do this. Okay, before I go over the next example, normally it says find the equation of the tangent, and this says normal. If you want to make a note that the normal is perpendicular to the tangent. Okay, so the slopes are going to be opposite reciprocal. Okay, what did we just find our slope to be? Look right here. We found this says the slope at f, the slope of f when x is 1 is 1/4. Okay, so the slope of the tangent at 1 is 1/4. So if we know that, let me make a little note to you. If the slope of the tangent at x equals 1 is 1/4, then the slope of the normal at x equals 1 is -4. We took the opposite reciprocal. Okay, so we know now that we're dealing with -4 as our slope. We also need an ordered pair. We know that x is 1. So if we start writing our equation, we know that it's going to be y minus, I don't know what the output is, but I know that the slope is -4, and I know that my x is 1. So I can do that. Now I need to find in this spot the output of f at 1. The reason I'm saying 1 is because that's the input and that's what they said. So off to the side here, how about we find f of 1? Function f was given above in the beginning, and it's 1 over 1 plus 1, which is 1/2. So then I can throw 1/2 in. Okay, so again, if they ask for equation of the normal, you're going to treat it just like you're doing the tangent, but instead of using the slope of the tangent, we want normal, we take the opposite reciprocal of that and get -4. Okay, on to 3. Match each of the following represents the derivative. Oh, we did this before where we had to match things up. Well, remember what the alternative form looks like, and it looks like the limit as x approaches c of f of x minus f of c all over x minus c. Now this is so much easier than what we did before. Look here, the way that this matches up. X approaches 5, x approaches c. So c has to be 5. Done. Also, x minus 2 cubed is the first part, which is f of x. So f of x is x minus 2 cubed. Okay, this one is easier than the one we did with the other form. If I'm matching this up again, if I look here, that is a -3. And then if you look over here, that's what this number is. So x approaches c, so c is -3. And then let's use a different color. This right here matches up with this, which is f of x. So f of x has to be the square root of x plus 9. Okay, awesome. So that was easy. Okay, going on. Here's how we can look at differentiability at a point x equals c. So we're saying a function is differentiable if and only if. And look what happens here. We're used to this. We're used to the left having to equal the right. Notice this alternative form. We don't have h. We have x approaching a number. So this is a nice way to categorize this, and it just says, or to summarize it, it says that to be differentiable at a point, the graph has to be continuous and smooth. So we'll look at some cases that aren't continuous and smooth. Okay, you'll see sometimes, you'll see the word locally linear or the phrase here. And what this means is, so remember we want to be continuous and smooth to find derivatives. Locally linear means, let's draw a couple graphs here, just on the left. If I draw a parabola right here, okay, and let's say I box this piece off, and I hit zoom on my calculator, like I really zoom in on that, do you get that it's going to look like a line? Okay, so the example here is f of x. If I look at f of x equals x squared, and if I zoom in, then the function is going to look locally linear. Okay, if I take another function, okay, so if we look at this function, and if I zoom in, so if I zoom in some pieces, like if I zoom in right here and reconstruct that, of course that looks linear. But do you guys see a section that you could zoom in that will not look locally linear no matter what we do? What if we zoom in right here? Okay, so if I take that, zoom in on my graphing calculator, I'm still, so if this scale was here was 1, so let's say I zoom in and now it's 0.25. So I'm really close now. This area in the middle is still going to look like a V no matter what I do. Okay, so because of that, on the left here, this is not locally linear at 0. So the derivative wouldn't exist at 0. However, this piece, no matter where I zoom in, I can get little pieces that look straight. So back here, when it says smooth and continuous, this piece right here is not so smooth. Okay, it's a corner. It's not smooth. I just wanted you to be aware of the words locally linear and what they mean. Okay, here are the 4 cases. You have to memorize this, that derivatives will not exist. So this first case, if you have f of x equals absolute value of x. Notice that the domain is all real numbers, right? So it's not a domain issue. It's the fact that at x equals 0, f of x is not locally linear. Okay, if you look right here and zoom in, there's no way we can make that locally linear. Okay, so it's not smooth. Another case, right here, not so smooth. What happens in this case is if you have, this is the graph of y equals x to the 2/3. Again, the domain is all reals. However, the derivative is actually 2 over 3x to the 1/3. So when you look at the derivative, you can see in the denominator, if x is 0, y prime won't exist there. So that's another reason why at 0 the derivative doesn't exist. Visually we can see there's a cusp, but if you look at the derivative itself, you'll see that you have an issue with 0 in the denominator. The third case is the vertical tangent. So this is the graph of the cube root of x, which is also known as x to the 1/3. If you look at this derivative, you're going to get 1 over 3 x to the 2/3. Now in all these cases when I'm saying, oh, look at the derivative, we're not finding it. I'm just telling you what it is. Do you guys see also in the bottom that we can't have 0 here? Okay, so at 0, the derivative won't exist. If you go to try to draw a tangent line in there, you're going to get a vertical one. And what's the slope of a vertical line? It does not exist. The last case, we've had issues with this since limits. If the left and the right limits don't meet up, or if we have any kind of discontinuity, then we won't have a derivative at that value. Okay, so at this point right here, at x equals 0, that is when the issue is. Okay, so all of these were x equals 0 that had issues. Let's go on to 4. It says find the derivatives from the left and the right. So here, if you want to make note, 4 and 5 both ask for derivatives from the left and the right. That is going to be a clue that we're going to be using the alternative form. Okay, so in both cases, that's what that means. So and then it says, oh, look at what it says after that. Is the function differentiable at x equals 3? Okay, if you look up here, I believe we said it earlier, that in order for a function to be differentiable, the left and the right have to be the same. So this is really asking us to find the left and the right. So notice, even if they didn't specifically say find the left and right, if they ask this piece about a function being differentiable, we have to know to do that. Okay, so let's do 4 together and you'll do 5 on your own. So let's find the limit as x approaches 3 from the left. Remember, this is different than what we've done before with h. Now we're letting x go to the number. It's going to be the function minus f of 3. F of 3 is 3 minus 3 over x minus 3. So that gives us the limit as x approaches 3 from the left of x minus 3. This second piece right here goes to 0. Do you guys remember this from chapter 1? What I wanted you to do on that one was think what's right to the left of 3 on the number line. It's 2.999. If you sub a 2.999 into the top, you're going to get 2.999 minus 3, which is a negative super small number, but because absolute value, it becomes positive. So we have a positive super small number over, again, we're subbing in the number 2.999 minus 3. That's going to be a negative super small number. Again, I'm not counting zeros. This is just a thought process. We don't even really need to write this down. Okay, so that is going to be the same number over itself, except one is negative. We get negative 1. If you look at the next part, they ask from the right. Limit as x approaches 3 from the right. It's f of x minus f of 3 all over x minus 3. 3 minus 3 is 0. That's gone again. So now we are looking at the limit as x approaches 3 from the right of absolute value of x minus 3 over x minus 3. If we're thinking of now 3.0001, right? It's right to the right of 3. If I sub that into the numerator, 3.001 minus 3 is a super tiny number. Absolute values mean nothing over the same tiny number, because 3.001 minus 3 is that. Same thing over itself is 1. So look what happens. We found the limit from the left. I'm sorry, we found the derivative from the left. We found the derivative from the right. They are not the same. We just saw above, look again, right here, that if the left and right derivatives are not the same, function cannot be differentiable at that value. It's not to say that it's not differentiable everywhere, just at x equals 3. So we would say f of x is not differentiable at x equals 3. Notice we're only talking about x equals 3. I don't think it was negative. Let's fix that. Okay, you guys keep writing while I'm fixing this. And we would say at x equals 3 because the derivative from the left, I wish I had a little more space, is not equal, I'm going to write super tiny, the derivative from the right. Okay, I hope you guys caught that. If you go to graph it, this function is shifted 3 to the right. It looks like this. Okay, do you see the corner that you have? This, remember, derivatives don't exist at corners. So that's another reason proving why the derivative does not exist at x equals 3. We showed using left and right hand derivatives. You can also see by looking at the graph. Okay, 5 has a little trick to it, so pay attention. You can after you get past the trick, you can finish it on your own. Looking at the first one, derivative from the left and the right. So let's take the derivative 2 from the left. And 2 from the left, we're going to use the function less than 2, which is this one. So we are going to use 1/2 x plus 1 minus, now it says f of 2. That's what should be next. So this is the tricky part here. F of 2 is when x equals 2, and it's this one. So we are going to replace x with 2 in there. Okay, all over x minus 2. So keep going on, and that is a positive 2, not negative. I want to take that negative out. Okay, so 2 from the left. We have 1/2 x plus 1 minus 2 over x minus 2. Clarifying the top, simplifying this. 1/2 x minus 1. We're expecting, if we use direct sub, remember guys, even if it's coming in from the left, if we can try subbing 2 in and if it works, but we're actually going to get 0 over 0. So we're going to keep going. The limit as x approaches 2 from the left. I'm going to factor out 1/2. I'm going to get x minus 2 over x minus 2, exactly what we would expect, and we get 1/2 as our answer. Derivative from the right. Before I go on, I really want to make sure what you understand what we did. This is f of x minus f of 2. So for the f of x, we're using to the left of 2, so I'm using this. This is specifically right here asking us for f of 2. F of 2 is found whenever x equals 2, so I sub a 2 in. Okay, that part was the tricky part, so if you didn't get that fully, let me know when I see you next. 2 from the right, x greater than 2, I'm going to use the bottom. So I'm going to write root 2x minus f of 2. F of 2 was when x is equal to 2, so that one. So that is also going to be the square root of 2 times 2, all over x minus 2. So we get the limit as x approaches 2 from the right of root 2x minus 2 over x minus 2. Direct sub, that's going to give us 0 over 0. So we know what to do. This is one of the things we learned in chapter 1. We are going to multiply by root 2x plus 2. We're going to rationalize the numerator, and we get the limit as x approaches 2 from the right. If we FOIL the top out, we are going to get 2x minus 4 all over. We leave the bottom factored. We're hoping to factor that x minus 2. I'm going to factor, let's draw a line here. I'm going to factor a 2 out of the numerator and get x minus 2. There we go. It is now going to cancel with the x minus 2 in the denominator. So then these guys cancel. And now I'm going to get the limit as x approaches 2 from the right of 2 over the square root of 2x plus 2. I'm going to clean up my fraction bar. Just got a little carried away there. And now you can use direct sub, even though it's 2 from the right. If we can sub a 2 in, we're good to go, which we can. So we're going to get 2 over 2 plus 2. I got that because I subbed a 2 into this x, which gave me the square root of 4. This is 2 over 4, which is 1/2. Did we answer the question, though? So we found the derivative from the left and the right. Is the function differentiable? Yes, f of x is differentiable. We don't know, but we're not looking at everything. We're just looking at 2, so that's what we're going to answer. Because, and then you want to say the left and right derivatives are the same. I'm going to hope I can squeeze this in. You know what, maybe if I get rid of this line, that might help. So because the limit as x approaches 2 from the right, and then I'm going to write the alternative form, is equal the limit as x approaches 2 from the left, and then I'm going to write f of x minus f of 2 over x minus 2. This looks a little squeezed in here. The answer key online is written a little nicer. You might be able to read that a little better. Okay, going on to 6. Why don't you guys try 6 now that we know this whole trick with piecewise? So when we're looking, when we go to set this up, and to determine, one more other thing before I go on, to determine if f is differentiable, what that really is saying is the left and right derivatives have to meet up. So you have to know that that's what they mean. Also, because of that piecewise, we have to look for the trick. So let's take the limit as x approaches -1 from the left. It's going to be the function. So the function to the left of -1 is the top one. So 2x minus 1 minus f of negative 1. F of negative 1 is what happens when x equals negative 1, which is also the top one. So this is going to be minus 2 times negative 1 minus 1 all over x minus negative 1. So then we get the limit as x approaches negative 1 from the left. We get 2x minus 1. And then if you look inside here, this is negative 2, so negative 3, but the minus making it plus 3 all over x plus 1. Then we're going to get the limit as x approaches negative 1 from the left. 2x plus 2 over x plus 1. Direct sub with negative 1. Again, even though coming in from the left, we don't care. So we're going to take the limit as x approaches negative 1 from the left and take out a 2. And again, we actually didn't even have to worry about this whole thing of negative 1 from the left because they canceled, and you just end up with 2. Okay, going on to the next one. They asked about differentiability, so we have to know to check both sides. So negative 1 from the right, we are going greater than negative 1, and we're using this. So 2x plus 1. Now minus f of negative 1. What that means is that I'm going to sub in a negative 1, and negative 1 is where it's equal. So it's going to be 2 times negative 1 minus 1 all over x minus negative 1. Limit as x approaches negative 1 from the right, 2x plus 1. Let's look inside here. Negative 3 minus, that's plus 3 all over x plus 1. The limit as x approaches negative 1 from the right, we have 2x plus 4. Okay. If I try subbing anything in, look, if I factor the top, it's not going to help. I'm going to get 2x plus 2 over x plus 1. Nothing is canceling. So what I'm going to get if I sub a negative 1 in, I'm going to get 2 over 0, and that really doesn't go anywhere. Okay, so we know the limit here does not exist. And we're really just trying to compare answers. Okay, we're trying to compare these two because we would want them to be the same. If they were, we have differentiability. Because they're not the same, f is not differentiable. So I know I talked about this continuity argument. I'm just going to walk you through that. So we would say since the limit as x approaches negative 1 from the left, and then we have to use the definition here, is not equal. I'm going to carry it on. It would be nice if it was all lined up. It's just hard writing on this. So again, if you look at the answer key online, it's written a little nicer. Because they're not equal, f is not differentiable. At x equals negative 1. Okay, what the continuity argument said is, I'll come back to that. Let's go down to the bottom. What this bottom says, if a function is differentiable, then the function must be continuous. Okay, but the converse is not always true. So what I mean by that is look at this function. Isn't this function continuous? I never picked my pen up, but is it differentiable everywhere? It's not. Okay, this function is not differentiable right here because there's a corner. Okay, so because of that, so just because a function is continuous does not mean it's differentiable, but if a function is differentiable, it has to be continuous. Okay, so make sure you guys have that down. What this is saying on this part when it says the continuity argument, all it's saying is that if you could prove that a function is not continuous, then it doesn't have the chance at being differentiable. Because to be differentiable, you need to be continuous. Okay, I can see if I can try to squeeze some of that in. If not, we can just talk through it in class. Okay, so let me try, but again, we're pretty much done here. To prove continuity, so this is completely separate from left and right derivatives. Wouldn't we need to find the limit as x approaches negative 1 from the left? So if you guys go up to the problem, negative 1 from the left would be to using this. So 2 times negative 1 minus 1. Let's go back and write that. So that would be 2 times -1 minus 1, which is -3. Okay, then if you take the limit as x approaches -1 from the right, okay, so now I'm going to use the bottom part. -1 from the right would be subbing a -1 in of f of x. You're going to get 2 times -1 plus 1, which is actually going to give you -1. Okay, so because the left and the right, let's circle these, because the left was -3 and the right limit, notice these are not derivatives, these are just limits, but because the limits aren't the same, then the limit doesn't exist. If the limit doesn't exist, if you remember from chapter 1, function's not continuous. If a function's not continuous, it's not differentiable, okay, at that point. Okay, that wraps it up, and we are all set. Any questions in class, let me know.